Welcome to Quintus Technologies Tech Talks. I'm Chad Beamer, Applications Engineer for Quintus Technologies. And today we'll be interviewing a well-known professor and graduate research associate for the Ohio State University. Thank you both for being with us today. Could you introduce yourselves, the university and department you represent?
I'm Colleen Hilla. I'm a PhD candidate in the welding engineering program at The Ohio State University.
I'm Mike Mills. I'm a professor in the material science department at The Ohio State University.
Excellent. And can you go into a little bit of detail about the department you represent and some of the aspects associated with your facility and the work you focus on?
Absolutely, Chad. Thanks very much for asking. The Department of Material Science at The Ohio State University is one of the largest material science departments in the U.S. It has activity areas in all of the major areas of material science and engineering. We have core activities and what we think represent fundamental aspects of material science, that is materials characterization, computational material science, corrosion science, and materials joining and welding. And that materials joining welding aspect is associated with the work that Colleen is doing on additive manufactured superalloys. We also have other activity areas in application areas for materials, that is structural materials, ceramics, sensor-based materials, biomaterials, polymers, and electronic materials, photonics. So we have actually a growing department. Over the last 10 years. We've grown substantially. We have a large number of younger junior faculty, younger than me, that have joined us. So we're up to about 38 or 37 tenure track faculty. We have about 19 of those faculty have joined us in the last 7 years or so. We have a very large undergraduate and graduate program. We have about 380 undergraduate students presently. That includes material science and welding engineering, and about 230 graduate students presently. So a very dynamic and multifaceted department. We're also highly ranked. We're ranked 12th in amongst undergrad programs nationally, and 13th amongst the graduate programs. And so we're in the midst of very, very strong efforts in this area nationally. So we have activity areas specific to this talk that would be of interest in structural materials, that is materials for aerospace, for turbine engines, for example, and that is potentially one of the application areas for this work that we'll be talking about today. We also have activity in casting, light metals manufacturing, and also very new areas, the area of hybrid autonomous manufacturing, where we use robots and additive deposition systems to create materials that have never been created before. So all sorts of exciting aspects there. We also have world-class facilities and characterization, and that's something that I focus on personally, and Colleen is taking advantage of extensively. The Center of Electron Microscopy and Analysis at The Ohio State University is one of the best centers in the world for doing electron microscope observations of materials microstructure. And finally, we have a very strong computational modeling group where we deal with length scales of materials all the way from atoms on up to size scales approaching those components of materials, and try to understand the relationship between microstructure, processing, and properties at all of those length scales. And this is where we bring together modeling activities with, for example, the characterization activities that I just mentioned. The welding engineering program at Ohio State University is totally unique nationally. There's no other comprehensive welding and joining program anywhere in the country, and it has important activity areas in welding, metallurgy, and materials characterization, welding processes and automation, non-destructive evaluation, and computational design and analysis. So really a broad, comprehensive program on the welding and joining of both metals as well as polymeric materials. We also have a very strong interactions and linkages with the Edison Welding Institute, EWI, which is basically co-located with the welding program at Ohio State. We share the same building. And EWI has fantastic capabilities in all sorts of important processing aspects and large-scale processing devices. And there are wonderful interactions of students and researchers crossing between the welding program and the EWI. And EWI has been a strong partner and supporter of the work that Colleen is going to be talking about today.
Let's jump right into it. Can you tell us a little bit about the additively manufactured Rene 65 effort and the motivation behind the work?
Yeah, so there's a lot of interesting benefits that you can get through additive manufacturing, but we found that there's a large technical gap in terms of looking at these higher gamma prime alloys, which are really useful for a lot of aerospace applications. One of the main issues with these alloys, though, is that they're not very printable. You experience a lot of solidification cracking and issues with printability. So what we found that is that Rene 65 does a good job kind of filling that gap. It's pretty printable, so we don't experience a lot of these cracking issues, and we can kind of study these higher gamma prime alloy systems using Rene 65.
One goal we see with additive manufacturing is to minimize post-processing, but these nickel-based superalloys are unique. Post-processing is critical to truly optimize the performance of the material. Can you touch on some of the post-processing that was evaluated in this project and the reasoning behind it?
Yeah, so these alloys in the wrought condition are all post-processed, so it's something we do need to do with the additive manufacturing alloys as well. The wrought alloy is completed in the subsolvus condition, and the reason for this is they experience pretty rapid grain growth in the supersolvus condition. For the additive manufacturing alloy, we evaluated both this subsolvus condition, which is kind of the traditional Rene 65 heat treatment, as well as evaluating the alloy in the supersolvus condition.
Interesting. And along with evaluating the supersolvus and subsolvus, there was also evaluation of applying rapid cooling within the HIP vessel. Could you explain to the audience the reason for exploring that avenue?
Yeah, so the ability for the Quintus machines to do rapid cooling is one of our big draws to this equipment. With these alloys, you get a lot of precipitate growth on cooling, so we can do rapid cooling or more controlled cooling. We have more of an ability to control the precipitation behavior, which is going to have a big impact on our mechanical behavior.
So the added functionality in the HIP system gives you an extra dial to kind of control or steer the microstructure. And kind of understanding the process and structure relationship then allows you to dial in the desired mechanical properties. Can we discuss in a little bit more detail some of the key microstructural findings along the way?
Yeah, so one of the interesting things in the as-built condition of these alloys, a lot of AM materials experience a directionally solidified microstructure in the as-built condition, where you see these long columnar grains parallel to the build direction. Depending on your processing conditions, you can also see transverse to the build direction, you'll see kind of this cuboidal lattice grain structure. And we're kind of trying to understand what causes that during the printing process. So we're able to do these single track and double track experiments where we can kind of see how this specific microstructure develops over time and why we only see it in certain conditions and not in other processing conditions. We also found, which is very interesting, in the supersolvus heat treat condition, as I mentioned, in the wrought version of this alloy, you experience very rapid grain growth in the supersolvus condition. We found very interesting that we don't see this in the subsolvus condition. Looking at even up to an 8-hour hold time, we don't see grain growth. It kind of opens up a whole processing window that we don't see in traditional manufacturing.
Interesting. And after hipping these microstructures, specifically the super solvis, do you see a resulting more equiaxed microstructure, something that is significantly different from the as-printed condition you had mentioned?
Yeah, so what we found is in the subsolvis condition, you have grain pinning. So we're able to, through use of EBSD, where we can look at the different orientation of each grain, get a mapping of our different orientations and our different grains. And we can kind of see that in the subsolvis condition, we maintain that directionally solidified microstructure. We have more of a bimodal precipitate structure, and then we have still pretty high strain in the material, which you kind of develop during printing. In the supersolvis condition, we develop recrystallize the grain, so we have a equiax grain structure, pretty low strain in the material, and then we were able to get kind of a fine homogeneous precipitate structure, which is something we're able to control kind of the size of that structure with the cooling control available through HIP.
And would we say equiax structure is more desired from a design standpoint to be able to predict behaviors in different orientations?
Yeah, so it'll give us more uniform behavior comparing different orientations. In the as-built and the subsolvis heat-treated condition, you're going to get different behavior based on your loading direction because you have it's kind of seeing different microstructures. Whereas in the supersolvis, we have an equiax grain structure, so no matter what your loading direction is, you're going to have a pretty similar behavior.
So this has gone to show that post-processing is critical in getting the type of structure you desire, the type of precipitation you desire for your mechanical properties. So we've talked about the processes, we talked a little bit about the microstructure. Can you go into depth on the resulting mechanical properties?
Yes, we've seen some very interesting mechanical behavior, particularly when looking at creep, which is the critical application for a lot of these higher gamma prime alloys. We found that using the supersolvis heat-treated condition, we can create microstructures that have behavior that are superior to that even of the wrought condition. We also found that using HIP, we can even push that into that behavior window even further, comparing the traditional solutionizing heat treatment. We have much better behavior both in the subsolvis and in the supersolvis when using HIP. We kind of seem to see that the main reason for that is during testing of the solutionized material, we get grain boundary decohesion and a large amount of cracking, and this seems to be fixed through using HIP. We don't see this large amount of cracking during testing, which is having a huge impact on our mechanical behavior.
Very interesting. So what's the significance of these findings?
Yeah, so this is great for both additive manufacturing and for kind of qualification. In terms of additive manufacturing, if we see these superior behaviors coming from these microstructures, which you have a little bit more control over through additive manufacturing, we're seeing better behavior that opens up kind of the application window that for uses of additive manufacturing. In terms of HIP, some of the issues that still exist within use of additive manufacturing is kind of a qualification. If you're having some builds that are behaving better than others, if we're able to kind of create a more homogeneous structure through HIP, where we see more uniform behavior, this is great in terms of part qualification.
So a more reliable material and a process that gives you maybe a robust route to obtain a structure and property that you desire. This is some great work that you're showcasing. What are some of the next steps in this effort?
Yeah, so we're kind of expanding our testing, especially on the creep behavior, so creep materials, so looking at room temperature as well as high temperature tensile testing, as well as expanding our tension creep efforts. We're also have a robust modeling program going along with this to kind of understand how these microstructures develop over time and kind of how they're going to impact our mechanical behavior.
Well, we look forward to seeing what's to come of these further developments, and Quintus Technologies is here to support your efforts along the way. Thanks again for working with Quintus Technologies, and we look forward to your ongoing R&D efforts.
Yeah, thank you for letting us present this work and for working with us as well.
Thanks very much, Chad, and thanks to Quintus for your support.
Colleen, Mike, you're welcome.